It's also my great pleasure to introduce our last speaker, who is our very own Mark Risjord, who is also a member of our research project on inferentialism, naturalizing inferentialism. Mark Risjord is a professor at Emory University, and he will present a talk entitled Inference and Scientific Representation.
Thank you, Laco. Dobrý den, kolegové. It's so nice to speak to you. I really wish I could be there, but things are what they are. Perhaps again sometime soon. So I'm really eager to share with you this work that we've been doing. I've been doing this along with my colleagues, Kareem, Khalifa, and Millson. And we're working on a problem in the philosophy of science, but as you'll see, there's a very interesting connection with inferentialism. In our project, we're addressing a problem of scientific representation. And in the first part of my talk, I'm going to give you a really quick overview of what that is and why inferentialists ought to be interested in it. And then I'm going to present our intervention in this, our inferentialist view about scientific representation. And in the latter part of the lecture is the real work, and this is brand new stuff, really at the workshop level here. But we want to develop a kind of expressivist view, and I hope to make clear why that would be valuable and important in this area, and in fact quite challenging, much more challenging than I anticipated as I went into this. So let me begin with the problematic of scientific representation. One of the things that's happened in the philosophy of science over the last 30 plus years is a shift from philosophers of science thinking about theories as the main sort of scientific product we want to focus on, and a shift from that to models. And one of the important features here is that theories, especially as mid-century philosophers of science thought about them, were taken to be linguistic objects, and theories represent in just the same way that language represents, and philosophers of science help themselves to all kinds of ideas from the philosophy of language that articulate that. There was no special problem of scientific representation. As they shifted to models, and I don't really have time to go into this shift or why people said it, the idea is that scientific models represent differently. They do not represent in a linguistic way. So the answers to questions about how language represents don't tell us how models represent. And here on the screen, I've got just an illustration of models from across the intellectual world: physics, chemistry, biology. I'll talk about this one in a little bit. This is something from social psychology. This is something from sociology. And what all of these have in common is an attempt to understand a phenomenon by analyzing it into parts, elements, and then saying something about how those parts interact, by what process the phenomenon you're interested in comes about. Variously related to theory, this sort of thing is very closely related to Newtonian mechanics. These, the Lotka-Volterra equations, actually are very atheoretical. They're very much a ground-up model. So as philosophers of science have approached this kind of problem, the main question is, in virtue of what does a model represent a target? And target is kind of the generic technical term for whatever it is the model is supposed to represent. So presumably this represents some sort of molecule. But of course, models misrepresent, they idealize, they abstract. There's a lot to say about how they do that, but they're very distorted, and intentionally so. So the main question is, how can we learn from them anyway? And the main mechanism by which we learn about models, according to philosophers of science, is what's called surrogative inference. And the idea here is that we inspect the model, we maybe do some calculations with it, or we just kind of manipulate it. And by looking at the model, we then learn something and apply it, make an inference from the model to the world and say, okay, the model says this, so the world must be like that. That's a surrogative inference. That seems to be the main mechanism that connects models to the world. So as philosophers of science have responded to this question of in virtue of what the models represent, there's been two, we can divide the field into sort of two broad approaches here, and I hope you'll see the connection with inferentialism right on the surface. So the main choice point is whether you are going to articulate a theory of scientific representation and then explain surrogative inference on that basis. And that's the dominant approach in the field. Most everybody thinks that's the way we have to go about it. There's a smaller approach, which of course us inferentialists are quite sympathetic to, which is first you figure out how inference works and you build a conception of scientific representation out of that. Now, in the substantialist side, there's a bunch of suggestions about what that representation relation might be. Models are similar to the two, or they resemble the target systems. There's some sort of structural iso or other morphism that connects them together. And some have just said denotation. Models denote their targets in something like the same way. And here's where it gets tricky. Proper names to denote people. Right? Notice these are all substantival in the sense they're postulating some sort of metaphysical even relationship between models and targets. And then on the basis of that, if that's in place, if the model really is similar to the target, for instance, then we could make the inference. Inferentialists, of course, want to talk about inference first. But here, if you go into this literature with the kind of inferentialist intuitions that I would go into it, I did go into it with, and at least some of you would, it's going to look really weird because a lot of the things that get called inferentialists are actually not not as full and as thoroughgoing as one would want. So the denotational species does make representation depend on surrogative inference, but they build denotation into it as well. So they're really not that different from the substantivalists. What we're calling, what you might call quasi-denotationists, and here, if you know the literature, I'm thinking of Mauricio Suarez. It's not denotation, but it's very pragmatic and almost pragmatist. That is, that scientists do a bunch of things in virtue of which the models get what he called at one point denotational force. So it's kind of denotation-ish, but then surrogative inference. What hasn't been developed and what we're working on is a properly, what we want to call thoroughgoing inferentialist view, where you build a conception of scientific representation right up out of surrogative inference. There's nothing else. There's no substantival stuff. There's no denotation going on. The only people who've done this there's one or two papers out there. In fact, our friend and fellow inferentialist Jesus Bonilla in Madrid has made this point that, look, if you come at this from philosophy of language inferentialism, this whole debate looks like it's broken, that you've just gone running off and tried a bunch of solutions that we already know don't work very well. But it turns out there's some real challenges here to actually developing a proper inferentialist view. So here's why I think inferentialists need to pay some attention, or ought to pay some attention, to scientific representation and the vocabulary of model represents the target. The going view in the philosophy of science is that this is not linguistic representation, it's its own thing, and it needs a substantive kind of answer. The kind of answer you might mobilize coming at it from a kind of Brandomian expressivist perspective doesn't have the materials there that you would work with. So that doesn't have, models don't have linguistic structure, they don't have the sort of things that Brandom uses to build out his account of semantic vocabulary, like it, true, refers, and so on. It's just not there. So how could you possibly do this? So is it even really possible to have a thoroughgoing inferentialism that would treat the operator and scientific represents, in expressivist terms? That's what we're going to try and do. So here's our strategy. We're going to try and, you can't do exactly what Brandom did, but we think we can do something analogous. So really, really broadly speaking, the Brandom strategy for thinking about semantic and logical vocabulary is to start off by specifying a set of kind of base entitlements and commitments, base inferences that the expressive vocabulary is going to capture in some sort of way. And then you specify the functional role of this operator in its relation to that vocabulary, that underlying base set of entitlements and inferences, such that you capture the sorts of things one says and one does with, say, the truth operator or the denotes operator. We're going to do that in the scientific representation area by starting off with surrogative inference, because that seems like that's the set of inferences, that's the set of entitlements that scientists use to move from models to targets, right? So that's the base. Now, then can we specify a functional role for model M represents target T with respect to that surrogative inference base that then captures its functionality actually in scientific discourse? Why do we even want to say this model represents that system or deny the model represents the system? Okay, let me begin by characterizing our version of thoroughgoing inferentialism and our account of surrogative inference. So surrogative inference is very common, easy to find examples. Anytime we're thinking about the weather these days, we're making an inference from a model to a target, right? This example over here, the model says that predator and prey populations can be in equilibrium. I'll talk about that in a second. It's a more kind of complicated, interesting example. But we don't need to get into any of the complications to see some of the things that are in the structure of justification for a surrogative inference. So the basic form here is the model tells us something. We've inspected the model and we've read something off of it, perhaps with calculations or perhaps by manipulations. And then we've drawn some conclusion about that's true or false of the target system in which we're interested in. Now, basic philosophy 100 tells us that there's two sorts of things you have to pay attention to in justifying this inference. One, does the model really say that P? So as a scientific matter, have we properly used the model to generate this premise? And then, of course, all of these inferences are ampliative inferences. There's so we have to be sure that in our background knowledge or what have you, there aren't defeaters lying around that would block this inference. That much we can read right off the form. To see the rest of the structure, we want to dig a little more deeply. So let's take a look at this particular inference. The model says that the predator and prey populations can be in equilibrium. The model over here on the left-hand side is the Lotka-Volterra equations, which were studied by actually independently a pair of mathematicians. It was known that animal populations went through boom and bust cycles, and one of the problems in biology was to explain why they cycled like that. Both Lotka and Volterra were interested in thinking of biology in terms of energy exchange. And so that led them to these equations. And so what these equations do is tell us that when you solve for X and Y together, obviously they're interlinked with the two equations, you get this pair of offset curves, right? The one rises followed by the rise in the other, the one falls followed by the fall in the other. Pretty interesting. Looks like we can use these to model predator and prey relationships because predator and prey are known to go through these kinds of offset cycles as well. But of course, the equations themselves are just uninterpreted math. They don't model anything. To model it, we've got to do something that in science is still called, at least in the social sciences, is still called operationalizing. You've got to find a way of, and this does not mean what Percy Bridgman said it meant, though he was in the same neighborhood. What you have to do is interpret the variables. So the X in this equation is the prey equation. X is the level of the population. Y is the level of the predator population. Then all these constants have to be interpreted in biological terms. So the alpha here is a coefficient that gives you the growth rate of the prey population. And then this is they say the fox is eating the rabbits. This is the foxes reproducing as they get more food supply, and this is the foxes dying. Now, interpreted in this way, we're able to get a derivation that says something interesting because there's a solution to these equations where basically you solve for X and Y, where X and Y are in equilibrium and they're non-zero. So there's at least one way of getting the growth rates and the death rates and so on balanced so that there's not the cycling between predator and prey, but that rather they stay in equilibrium. That's an interesting conclusion that falls out of this model. Now, operationalization really has two components. And what I just talked about, we call characterization. But if we were to apply this model and try to explain a specific event or test it against data, we'd have to do some measurements. The other part of operationalization, and this is often what the social scientists mean when they're thinking about operationalizing their models, is not just interpreting the uninterpreted math or what have you. It's also figuring out a measurement methodology that's going to be reliable in the context. Now, these again are scientific achievements. They're epistemic achievements. You have to make the argument that you've characterized it in this case, a biologically plausible way. And there's a century-long debate about this in biology. One of the problems here, and this is where issues of idealization start to come in, is that if you think of this as population growth, this coefficient is unlimited, right? There's nothing about the carrying capacity of the environment. You can't just let rabbits eat as much as they want. They're not going to grow infinitely. You're going to get to a point where there's just not enough food and their population is going to level off. This interpretation, this set of equations, or this set of equations as interpreted, doesn't represent that. Now, the question for the scientist is that limitation of this model an important one for my research project, right? So you've got a research question, and we think of as inquiry is guided by questions. And then the question is this model as interpreted an appropriate model for my research, which just means when I use it, will I get answers to the questions that are driving my research? So there's another status here, and that is relevance. You have to establish that the model that you're gonna use, in characterized in this way and perhaps measured in that way, is going to give you answers to your research questions. So again, this is an argument that scientists have to think through when they're modeling. Notice also relevance governs no defeaters, because the defeaters you care about in a scientific research project are precisely those that would distort the answers to the questions you ask. It may be that there's defeaters out there, but they just don't worry you in this kind of context. So relevance actually governs the whole structure here. So the justification of a surrogative inference depends on a whole set of epistemic entitlements to be established, what we call the inferential pedigree. And each of these is an epistemic status. And I really like yesterday's talks, both Molly and Hillary's talks, in the way that they were thinking about justification and the establishing of epistemic statuses of being justified as social things. And I think, and we're thinking about this as exactly the same kind of way. These are not individual states. It's not a matter of me being justified. It's a matter of making the philosophical or the scientific arguments and doing the measurements, constructing the model, what have you, so that these things are available. And once we've established that they're just justified, it's justified. We can all make these inferences now. And our claim is this is all you need for the justification of surrogative inference, right? So if you've got this, the inferential pedigree in place, all these entitlements have been secured, you're justified. But that now, we think, gives us everything you need to talk about scientific representation, that there's nothing really more to scientific representation than being in a position where you're justified to draw conclusions that speak about a target system. So now you might wonder, and this is, I think, is an important concern, why is this a story? Why is the story that told you a story about representation, not a story just about justification, right? What's this representation language doing over and above the surrogative inference stuff? And that's where expressivism seems it might do some real work for us. There's also a worry here that we've just, without telling a story about scientific representation, we've just snuck it all in the account of surrogative inference. So, and I want to address that as much as I can right now, and we'll come back to it really quickly. But notice that the story didn't invoke any of the scientific representation relations. There's no appeal to similarity or structural morphisms or denotation. Right? There's lots of representation going on, but it's all linguistic. And the ground rule in the philosophy of science is it's fair to have linguistic representation. Now, all these views assume linguistic representation and then say, and you have to do something else for scientific representation. It looks to us like we just did it with linguistic representation. Of course, the scientists have to represent, say, use semantic vocabulary, denote, yada, yada, but that's all done. All that work is done by language, and plug in whatever philosophy of language you like for linguistic representation. I like inferentialism. If you like truth conditions, plug it in. It doesn't really matter. Nothing in this view at this point is really depending on that. So then the question is, can we actually account for what representation does? And denotation too is a part of our project. I won't talk about it today, but we think we can get an account of an expressivist account of denotation as well. Okay, sorry, this is kind of breathless, but there's just a lot of stuff here, and I'm very, very excited about it. So this is the hot off the press, really. I mean, Jared and I were arguing about this hammer and tongs just yesterday afternoon. So my thinking is still very much evolving. Our thinking is still very much evolving about this, and I'd really like your feedback. This is I'm hoping this is a workshop. So let me start by articulating as our model Brandom's account of truth, and then show how we think we can do something at least analogous in the scientific representation domain. So Brandom treats truth as a disquotational operator, not as a predicate. So it's not characterizing a correspondence relationship, it's doing something. And the function, the special function of the truth operator is to license the assertion of a proposition that's been described or referred to in some sort of way. Canonically, quote, P is true if and only if P. What Brandom points out, and he's not the first person to think of this, is that this is an anaphoric, has an anaphoric function. That is, it gets its content, the proposition we're talking about comes from anaphorically picking out some other proposition in the discourse, the anaphoric antecedent. So let me say something quickly about anaphora. Pronouns, he, she, they, are canonical examples of anaphora. So Hannah walked into the store, she bought some cheese. We all understand that she refers back to Hannah. And this is the so-called lazy anaphora, where I can just replace she with Hannah. Hannah walked into the store, Hannah bought some cheese. It says the same thing. But the interesting thing is anaphora doesn't always work that way. So a woman walked into the store, she bought some cheese, we have anaphora. We understand, if you understand what I'm saying, you understand that she refers to the woman who's been indefinitely described here. But I can't just replace she with a woman, because then there's no longer a guarantee that this refers to the same person. Right, so this pronoun has got an anaphoric function that goes beyond just swapping into the name. Now, proforms come in all kinds of flavors. There's proverbs, there's prosentences, arguably. And then each case, what's happened is you inherit some kind of content from an antecedent somewhere else in the discourse. So applying that to is true, Brandom treats is true as a prosentential operator that anaphorically inherits its content from antecedent propositions and endorses that content. So if Hannah says, cheese is life, and Andrea says, that's true, then what Andrea does is taken up that content that Hannah expressed. Whatever commitments and entitlements are involved in the proposition, cheese is life, Andrea has now undertaken and endorsed those. Right. We can get quantificational. Truth allows this kind of quantificational antecedents too, which is super interesting and super useful. Right. Everything Hannah says about cheese is true. If I say that, I'm committing myself to all those propositions that Hannah has undertaken with respect to cheese, including the ones she hasn't said yet. Right. So now we have a whole bunch of expressive power that wasn't in our language before, simply through this operation of referring anaphorically to something else described by the discourse. Now, can we pull this trick with scientific representation? That's the $1,000 question here. So what's the function of M represents T, model M, target T? I think everybody in the philosophy of science and the scientific representation literature would actually agree with this. This is completely non-controversial. That the function of saying the model represents a target is to say that some surrogative inferences about that target are licensed by, justified by something that the model says, right? So that looks to us like a pretty plain Jane way of characterizing the function of scientific representational language. But this invites treating scientifically represents as an operator, right? And that's going to have an expressive function. So that means already we've staked out a position against the substantivalists in the philosophy of science literature. It's not so the represents relation is not characterizing a relation of, say, similarity, right? It's doing something else. And notice how it's inheriting content, right? The inferential pedigree is what tells us that the surrogative or inferences are licensed, right? That set of entitlements. And what's happening when I say the model represents the target is I'm taking on that entitlement, I'm asserting it in licensing and endorsing it, saying, yes, we're entitled to draw these some inferences from this model. Now, before we can blithely go down this road, we've got to be really clear that scientific representation is not the same thing as linguistic representation, and we can't just apply Brandom strategy without noticing some of the differences and dealing with those differences, right? So these disanalogies are important. The entitlements we're talking about with the inferential pedigree are epistemic, not semantic. And here's what I mean by that. In this case of something like is true, there's a proposition involved. So if Hannah says cheese and life, it's the proposition cheese is life, and whatever structure of commitments and entitlements, if we're thinking in inferentialist terms, gets us that. That's what I'm thinking of as a semantic entitlement or commitment. Now, when we're thinking about these scientific things, the entitlement to saying this model has been operationalized in a scientifically plausible way, it may well be true that we could tell a Brandomian kind of inferential story that would get us to that, but by the time we're done, we're going to have a whole lot more going on than the commitments and entitlements that are involved in propositional content. Right? It's going to involve a lot of stuff that's specific to scientific research and the kind of communities that are required for that. So it's going to be a much longer story. It's going to have a lot of philosophy of science in it, above the philosophy of language, and that's what's being picked up. It's not just a proposition or a belief. And then when you're endorsing it, you're endorsing that kind of entitlement. You're not endorsing a proposition. I'm not just licensing you to say something or licensing myself to say something, undertaking myself. It's a whole class of entitlements that this model is now going to let us, the class of inferences this model is now going to let us make. I think the one way of seeing how the rubber meets the road on this is that this idea of anaphorically picking up content. In some ways, I don't, honestly, I go back and forth whether this is a genuine case of anaphora or we have something that kind of walks and talks and smells like anaphora. And I think the best way to go in this is not to try and decide whether there's one or two kinds, but just to figure out what's going on with the epistemic, the scientific representation case. So in virtue of what does M and T pick up some kind of content from the inferential pedigree? Well, if you spell out the inferential pedigree in this kind of way, right? So instead of a diagram, I've written this out. Notice that how M and T are sprinkled throughout its characterization. And so what M and T have really done is picked out a particular, or maybe a class of really closely related, inferential pedigrees. So which pedigree, when I say M represents T, which pedigree am I talking about? That and how it and what is M and T doing there? It's picking out exactly this set of entitlements, wherein the target and the model were in the representational content of the language that's been built into the specification of the model has already done a whole bunch of work. So it's that work that M and T are picking back out. So we think of that as the relationship between the M and T, and M represents T, and the inferential pedigree. I think we can then capture what's going on with scientific representation in terms of the special function of the scientific represents operator. So here's sort of three usages of M represents T that you expect any account of representation to collect. There's actually, or account for, there's actually more. I don't have time to go into all those details. So in the case of M represents T, you should see where this is going, right? The function is that there's some set of surrogative inferences. I've kind of quantificationally picked up not everything that's been, it's unlike everything Hannah said. This is some of the inferences about T based on M are going to be justified, right? That's what I'm expressing. And notice that this is going to have already has a function over and above the justification of individual inferences. It says something about this model as operationalized and so on, that I can't just say by licensing a particular surrogative inference. We can also capture good and bad representation, right? Because this is just going to be a matter of, given a research project, right? This is always in the context of a research question and establishing relevance. It's to say that in the context of this project, there just aren't any interesting inferences that follow from this model. And this is what actually happened to the Lotka-Volterra models, that they turned out to be so biologically unrealistic that most biologists said they're really poor representations, right? They're really weak. I don't think there's a clear and bright dividing line in cases like that between it represents badly and it's just not a representation of, say, predator-prey systems at all. At a certain point, it's so useless and you have so many better ones that you just stop using it. But there are cases where you say, no, the Lotka-Volterra model is not a representation of, say, a certain chemical element, right? Why? Because you just can't make any inferences from that to this. Now, again, the justification is going to be program relative, right? You've established that this model is relevant to your research program. So maybe we could even say in some cases it doesn't represent T in the context of this research. A very differently constructed research might find a way to make it useful. So returning now to thoroughgoing inferentialism, we want to say, we want to stick with this, that something's a representation if and only if you've got justified inferences that are following from it. But now notice what the expressivist lets us say now in addition. The representational language in the scientific representational vocabulary here does not add any content over and above the surrogative inferences that are in the base. We're not saying anything new. We are able to do some things, but we're not saying anything new. So we're not adding to science, oh, models have to be similar or models have to be structurally isomorphic or something like that. Representation is not a substantive relation. So now we've got a basis for what Jesus and one or two others have wanted to say from an inferentialist standpoint, that actually the rest of the literature here is off on the wrong foot. You guys are all looking around for something that representation is going to stand for, and there ain't no such thing, right? Representation just functions to express entitlement to a number of inferences about a target system, and that's actually quite scientifically useful to be able to say, yeah, the Lotka-Volterra model just isn't a very good model of predator-prey relations, or, and this is actually an argument in biology, maybe it is, and so you can actually have the arguments at that level. So that's our story. I want to thank Kareem and Jared for being such wonderful and smart and critical co-authors, and I thank the Czech Science Foundation for supporting this research. And with that, we thank you.
Okay, so let me open Q&A. Anybody? Kirill?
Hi.
Yeah. Oh, Hilary first, then.
Oh, sorry. Oh, yeah. Really valuable and interesting work. I'm thinking of Paul Redding's inscrutability argument against Brandom. I wonder whether this can deal, whether the view you're proposing can deal with the iconic and indexical aspects of a diagram. So it seems like the conclusions we draw from a diagram can be explained in this way, but quite often with a really good scientific diagrams, we in future discover new things about a phenomena, because having endorsed the diagram, the iconicity allows new discoveries just based on that, mainly iconic, and also the kind of indexical things, even like something like the way that the periodic table allowed for lots of discoveries based on how people noticed how certain things are related to each other.
I'm embarrassed that I don't know the argument to which you're referring, and I've quickly written it down. It sounds like, from your quick description, it sounds like we do have an answer to that. Yeah, I think you can. I don't think those kinds of examples provide any serious problem for a Brandomian perspective, except to note that they are different from. I mean, so this is where I guess you'd agree. Yeah, the making it explicit doesn't cover these things, right? But kind of no surprise if you're thinking of this from the philosophy of language. Thank you so much for that reference. You said Paul Redding? All right, I'll be Googling in a few minutes.
Yeah, thanks for that, Mark. I wanted to ask you just a very broad question about what the goal of what you're doing is. Just because I think I missed something.
I talk fast.
So a number of decades ago, philosophers of science used to talk about scientific theories as a batch of sentences or propositions. They talked about evidence as another batch of sentences or propositions. They were interested in what the good inferences are.
Yeah.
Now, lots of people like to talk about models. And if you like the sentence or proposition view, there are certain kind of obvious things that you would say about talk about models, and which you could just translate it into relations between, right?
Yeah.
Right. So, you know, if I'm interested in how sea level rise might affect Manhattan, and imagine that I build, you know, something out of clay, you know, like Manhattan Island and its buildings and so on, and I stick it in my bathtub and I turn it on the tap and I see how far it goes up, and then I say, oh, this much sea level rise, you know, it's up to right? You can see what somebody who goes for propositions and right will say. Whether that gives a better or worse account than somebody who thinks directly in terms of models and skips it, you know, that's another issue. But it's until we get to the comparison, at a certain level of generality, it's pretty clear how to translate. And it's not clear yet until we do the comparison whether these are really, you know, just two ways of expressing the same thing, or whether there's actually real differences and one might be better than the other. And
yeah,
part of what you were doing when you're giving the sort of inferentialist view at a certain level of generality is, do you take this to be an argument in favor of an inferentialist account over various alternatives? Because I didn't see where you were making the relevant comparisons. Or were you saying inferentialists can give a way of, you know, talking about models too? Because it seemed to me that, at least at a certain level of generality, the idea that all of these different ways can give some sort of account of what talk about models is all about is bound to be right. And what I want to know is, are they just all interchangeable, or is there a reason for thinking that one of them does better than the other? And then I didn't see where you were doing the comparative.
Yeah, no, excellent question, and actually a couple of things to talk about there, and but I'll have to be brief. Let me start with the last. No, I didn't do any comparative work in this at all. In our larger project, that's exactly, and in fact, there's two kinds of comparison we need to do, and the one is, well, maybe it's all of a piece. But back to that diagram where I kind of had the tree structure, I think we can pretty convincingly argue that we've got a better account of what's going on with modeling than any of the competitors. And one of the key things in this is that all of those competitors appeal to users at a certain point in a way that's completely capricious, right? So it's a classic problem of, say, resemblance or similarity views, is that everything's similar to everything else in some way or other. And so the standard move is to say, well, actually modeling's not a two-place relation, it's a three-place relation. It's user uses M, user U uses M to represent T, and there's no constraints on the user. And so they're all subject to a kind of capricious user example. And insofar as they might want to say something like, well, okay, there's a whole bunch of scientific work that has to go on, it's going to screen out the users. Yeah. We can say that's actually should be part of the view. We argue that that's got to be part of the view, and our view is really the only one in the neighborhood who gets anywhere close to that. So there's a bunch of ways which we want to argue for our view over the other ones. In this part of it, it was just to try and secure the result that we actually can be expressivists, right? So the other conversation is with inferentialists like the one in this room right now, and to convince myself and me to convince my co-authors that we can actually do the expressivist trick and make good on a claim that a couple people have sort of gestured toward. Maybe I'll stop there. The first part of your question is exactly right. There's a story that has to be told, but in the larger paper that this is part of, this is a significant move we have to make, is to be clear about why there's a special problem with scientific representation. And that, I think, is less clear in the literature than it should be. There's actually debate about that. There's a few people who make moves, and there's a sense in which we want to say yes and no, because we are going to make the appeal that insofar as there's representational anchoring, it's all happening on the linguistic side. So there's no special extra scientific thing the scientific relation like similarity that happens. But at the same time, there is a special problem in the sense that you can't just get there from here. You have to say something else, and that something else is what we're putting in there. Thank you for that question.
Yeah, thanks a lot.
So perhaps the last question, Jaakko Reinikainen.
Okay, thank you very much. I don't know that much about this topic, but so my question is maybe a bit naive, but I was wondering if you have sort of a deflationist account of scientific representation in case of models, then does that sort of risk repeating the old Kuhnian problem of incommensurability between the models, when the models are being compared? Or do we need representation? Do we need to say more about representation in the semantic sense in order to make the comparison of models work? Or do you think that's not really important?
That's a super interesting question. It's not naive at all. Can you tell me the kind of context of comparison that you're thinking of?
Well, not really. Unfortunately, this is really sort of
okay. Well, let me get that one. Yeah. I see that if I see the question that you're driving at, and I think I do, or at least here's one. So we want to be able to say compare models that come from very different places. So the Lotka, and there are debates like this in the sciences. You'll have something like the Lotka Volterra equations and all this kind of mathematical biology, but this is one of these areas of the academy where the mathematical biologists don't talk a whole lot to the field biologists, and they'll have other kinds of models perhaps. Now I'm making it up, I don't know the biology well enough. And is there a way of comparing those so you can kind of say this one's better than that one, or this one really doesn't represent at all? What's crucial in our view, and what will make those comparisons make sense, is this relationship to the inquiry. And so in our larger project, we're working out, and one of the things that Jared Millson brings to this is an inferentialist account of questions, the logical questions and answers, and we're using that to actually give a lot of depth to a lot of things we want to say about scientific inquiry. And in the modeling case, all those connections in the inferential pedigree are going to be mediated by questions and answers, and whether you're obligated to answer this kind of question. So in the context of a particular inquiry, those questions about model comparison are real, right? I'm not sure they're really real. I mean, I'm not sure there's a genuine question, which is like, is the Newtonian model of the social system or the solar system a better model than the Lotka-Volterra questions? It's like, that just doesn't make any sense to me. I can't find a context where that would make sense. But is this, in the context of this inquiry about population biology, is this a better model than that one? And maybe they come from really different places and use really different resources. You can, there's what we can say, and I think actually most people who want to study scientific modeling want to say something along these lines, is that you may want to say, actually, for my purposes, this one does a lot better job, but we're going to say that's because it just answers a lot more of your questions. Or maybe both are good. In fact, maybe you need both because they pick out such different aspects of the phenomenon. And this is really common, and this is one of the reasons that modeling is a nice language for thinking about the sciences. Not that you couldn't have two theories of the same thing, but the language of theories is just a little more exclusive. We tend to think of theories as evolving from one to the other, not existing at the same time, though practically, in fact, they do. It's just easier to see with models like it is with maps. There's no big deal about having two maps of the same city that represent really different things. In fact, maybe even you can't find a simple and easy way to go from the one to the other. Scientific modeling works the same way, but from our point of view, if both are relevant to your inquiry, in fact, maybe both are even necessary to your inquiry, right? So you don't need to have kind of commensurability in the sense of being able to say, like literally translate the one or map from the one to the other when, does that sort of answer the kind of question you wanted to ask?
Yeah, I think I understand a little more about that now. So thank you.
Thank you.
Well, unfortunately, we are running out of time. Maybe there was one question or comment, short one, but.
Hey, thanks so much for that. This is Molly, which
Hi,
might
Molly.
make sense of my comment. You know, it's just this is just a clarificatory question about sort of what the like what we're getting out of giving the inferentialist spin on it that I just need some clarification about. And again, this is not like scientific modeling; it's not my domain. So here's just what I was thinking, and I didn't understand what the inferentialism was giving us over and above this. You know, models are funky because we might think that they're like theories, but they're not.
Mhm.
Because like we're abstracting and idealizing in all these kinds of weird ways. And that's because like what models are really like are like instruments, like in the same way that the thermometer is an instrument or a scale is an instrument. And just like, you know, there's a lot of different ways to construct a thermometer. There's a lot of different ways to construct a scale. We don't look into the scale and the thermometer and say like, oh, this is representing the world. Rather, it's the output of the tool that's giving us a representation of the world, right? It's the reading of the thermometer.
Yes.
Representation, and that those beliefs that we form on the basis of those outputs, the outputs of the tools are justified because the tools are reliable. And I was trying to figure out what the inferentialist spin was giving us over and above that kind of reading of models as scientific instruments like thermometers or scales or.
Interesting question. I'm going to have to think about that. I haven't thought about this in those terms, partly because I've come at this using my philosophy of science hat, not my, well, I don't own an epistemology hat. I own a philosophy of language hat, but I don't own an epistemology hat. I'll
lend you mine.
No, I think you do. Or at least I'll give you one. I'll buy one for you. I feel like I should have a back pocket answer to this question, but I find myself struggling with it. That's a good sign. There's something interesting going on here. It may be that at that level of abstraction, all of these accounts of modeling are doing the same thing, right? If we were only if we convince ourselves the only thing we should be concerned about in the philosophy of science vis-a-vis the epistemic questions was reliability, yeah, none of these differences would start making a difference. So then I guess this is as much and I really want to resist kicking this up to the meta level, but what it invites is a difference between the perspectives that epistemologists take on these kinds of questions and the perspectives that philosophers of science take. And I totally agree with Hillary that there ought to be a lot more crosstalk between those two subfields. And certainly in my education and early career, there was virtually none. I'm sorry, I'm blithering about that, but that's a really good question. I wish I was there. We could talk more about this, and I'd think of some things to say.
Thanks so much.
Well, let's thank Mark one last time for closing us out here.
And thank you.
Yeah, it's good to see you, Mark.
Yeah.
And then this is, I mean, you say you hope to have a chance to talk about this again. This is, we're 2 years through a 5-year project with YARDA, and so this is the first of at least 2 conferences. So we look forward to seeing you all again and staying in touch. There will be another one of these with more people in person. We understand that many people just simply couldn't come. We really appreciate those who did. And for those of you that are participating online, that often isn't easy either. So Thank you for that. Let me just say, I want to thank Petr Matejček, Michal Hubelek, and Petra Korbelova for helping us put this together. They did a lot of work. I think it went off very well. So please, let's thank them. And with that, we will say goodbye wherever you are in the world, and hopefully to talk to you again and see you all soon. So thank you again. Bye-bye.
Thank you.
Thank you. Goodbye.
Thanks for a great conference.
Thank you.